Robert is instead going to tell us about pseudo-holomorphic curves in the sixth sphere.
Okay. Thank you, Mark. Thanks to the organizers for inviting me. I'm actually going to talk about something that I thought about a long time ago, but recently thought about again because I was asked a question by Camilo de Leilas about the kinds of singularities that can occur for associative 3 cycles. And I was able to make progress on this, and I wanted to say what I had done. But a good part of it, I'll need to review some of the background on what the pseudo-holomorphic curves in the sixth sphere look like. And before I forget, let's see, let me make sure. Yeah, I just want to mention that the work there's been, ever since my original paper on that subject, which was inspired by Harvey and Lawson's calibrated geometries, there has been a fair amount of work, in particular lately, some very extensive work on the pseudo-holomorphic curves in the sixth sphere, and some of that is I'll draw on as I get to it. Let me say what some of the background is. It's been known now since over 60 years that the unit sphere in the imaginary octonians, which is homogeneous on the action of G2, actually has a natural, almost complex structure on the sixth sphere that's invariant under G2. It has 2 depending on the sign, but fix one of the signs, they're equivalent. And G2 acts transitively on the sixth sphere with stabilizer SU3, so the actual tangent space at each point you can think of as a copy of C3 with a particular complex volume form fixed. Although the almost complex structure is definitely not integrable, but still there are plenty of local pseudo-holomorphic maps from curves. That is, if you take any real analytic curve in the sixth sphere in R, then it extends to a pseudo-holomorphic map on some domain in R neighborhood in C into S6. But there are no higher dimensional almost complex manifolds. It was proven originally by Gray in the sixth sphere. It's as far from integrable as you can get. However, it's natural to, if you just forget everything except the almost complex structure, in fact, you can recover the action of G2 because it's a result that if you take any open connected set in S6 and any map into S6 that's almost complex, then either it's constant or it's the restriction to U of a left action by an element of G2. So the geometry of G2 is intimately connected to the pseudo-holomorphic curves. Some basic properties. One is that even though S6 is not a Kähler manifold, the pseudo-holomorphic curves are actually minimal in S6. However, unlike in the Kähler case, they can't be calibrated even locally. That is, there's no open set supports a closed 2 form that calibrates the almost complex curves sitting inside the open set. So they're not calibrable, but it's still, and obviously globally they're not minimal because, for example, a geodesic 2-sphere, certain geodesic 2 spheres, as I'll get to in a minute, are actually minimal surfaces, and of course they're not minimizing in S6. There's no homology in dimension 2 in S6, so they couldn't be homologically minimizing. However, the cone on such a curve is associative, and therefore, as Harvey and Lawson showed, is actually minimizing. So the cones are minimizing, and the interesting question is, what can you say about the structure of the singularities of associative things? Well, if you blow up and look at a tangent cone, then that tangent cone is a cone on, in fact, a cone on a pseudo-holomorphic curve in S6. And so what you would expect is that the singular locus of an associative guy, well, by Omgren's big theorem, the singular locus has Hausdorff dimension at most 1 for an associative. And when you blow up and look at a cone, you would expect to be able to see singular lines. In fact, we know one can prove that that any real analytic curve in a G2 manifold can be the singular locus locally of an associative threefold. But the question that I was asked by Delalis was, is it possible for that curve to just stop somewhere? That is it possible for the associative cone an associative cone to have a half line of singularities rather than an entire line? First, let's look at a couple of examples. As I said already, if you take any associative 3-plane in imaginary O, then its link is almost complex. It's a totally geodesic 2-sphere. And there are other examples. If you take a surface that sits inside an actual S5, a totally geodesic S5 sitting inside the 6th sphere, it turns out that's pseudo-holomorphic if and only if it's the cone on a special Lagrangian. If and only if the cone is special Lagrangian in that C3 for the complex structure that U determines on that hyperplane sitting in R5. And so, of course, you can take unions of these things, but for example, if you take a union of a bunch of planes, then because they're invariant under the antipodal map, they can't just intersect. I mean, their intersections have to be invariant in the singular map, so you can't so you can't get a half line. There's an example that doesn't lie in any hyperplane, which is the so-called Borufka sphere. There's a linearly full pseudo-holomorphic curve sitting in S6 that has constant Gauss curvature k equals 1/6, so it has area 24 pi. It's homogeneous under a maximal subgroup SO3 and G2 that acts irreducibly on imaginary O. This was written down by Sekigawa, but it's also invariant under the antipodal map. It's not hard to show that it's invariant under the antipodal map. So, for example, taking this sigma union one of these planes, you can easily construct things that are singular, but the cone will have an actual singular line, not a half line. The question is, can you construct something that will have a singular half line? Let me review very quickly how you can get your hands on a lot of pseudo-holomorphic curves. There's this notion of a Frenet frame. That is, if you take a pseudo-holomorphic compact curve sitting in S6, you get the pullback of the tangent bundle splits into 3 complex line bundles, sort of the tangent, normal, and binormal. And together with that, you get holomorphic sections of, for example, tau, which is T phi times the canonical bundle, is actually the differential of phi, the first differential of phi. Nu is like the second fundamental form, and beta is like the third fundamental form. And because the tensor product of these 3 line bundles is isomorphic to the pullback of the third exterior power, which we know is trivial, this tensor product is C. So in particular, if beta is not 0, I should have said tau and nu are not 0 as long as the curve is nonlinear and not constant. That is, by nonlinear, I mean doesn't lie in a geodesic 2-plane, 2-sphere. So if beta is not 0, if you take tau cubed times nu squared times beta and multiply that all out, you'll see that it's a section of these guys tensor the 6th power of the canonical bundle. And so you get an equation of divisors that says that 3 3 times the divisor of tau plus 2 times the divisor of nu plus 1 times the divisor of beta is 6 times the canonical divisor for a compact curve. And of course, the degree of the canonical divisor is 2 times the genus minus 2. And of course, because these are holomorphic sections, these are effective divisors. So in particular, if G is 0, that is, if it's a rational curve, what I'll call a rational curve, that is C is P1, then this side is negative, and whereas this side is necessarily effective, so beta had to be 0. So in that case, this third fundamental form has to vanish. If GC is 1, for example, then of course this guy is 0, and if beta is not 0, then in fact there can't be any ramification at any order for the curve. It has to be smoothly embedded, smoothly immersed. And if GC is positive, then beta not 0 implies that even in that case where you don't get any contradiction, or you get that the ramifications of that is the vanishing divisors of these first and second and third fundamental forms are bounded. Now, the nice thing is that there's an interpretation of beta equals 0. You might think, for example, if we were talking about CP3 and we did this construction in CP3, beta equals 0 would mean that the curve, it lies in a CP2. But there are no complex 4-dimensional subvarieties of S6. So beta equals 0 can't mean that. Can't mean anything like that. But it does have a natural interpretation. Remember that an oriented 2-plane in this R7 imaginary O corresponds to a unique null line, x plus iy, if you write E as x wedge y, where x and y are bases. It corresponds to an orthonormal basis of E, oriented orthonormal basis. Then this null line sits in the null 5 quadrant, sitting in the projectivized complexified imaginary O, which is a CP6. And E is in fact a complex line with respect to this unit vector in S6. That is, pi E is x cross y divided by the norm of x cross y, if you didn't normalize the basis. So, and the fiber of pi, so pi is now a map from the basically Q5 to S6. The fiber consists exactly of the lines in the tangent space at U to S6. It's a CP2. So if you have now again a complex curve, pseudo-holomorphic curve, then the binomial line is an oriented 2-plane in imaginary O, and so we can regard it as a null line in the complexified tangent space, in the complexified imaginary octonions, and you get a lifting B phi from C into Q5. So there's if beta is well, you always get this. There's always a lifting as long as it's a nonlinear curve. The lifting is well defined, but it turns out that this lifting from C into Q5 is holomorphic if and only if beta is 0. Beta is identically 0. Should be equivalent, identically 0 here. And this is a little weird. Of course, S6 is not complex, but Q5 is complex. Of course, the map from here to here is not holomorphic. It can't be, but it's partly holomorphic. It's horizontally holomorphic, which I'll get to in a minute. Anyway, in fact, it turns out that this lifting is not just any old random curve in Q5, but it's a curve that's tangent to a certain holomorphic 2-plane field sitting in Q5. 2-plane field on Q5 that's totally non-integrable. And here just a few results about this. If you have a holomorphic D curve, that is, if you take any holomorphic curve that's tangent to the to the two-plane field D sitting in Q5, then its projection is pseudoholomorphic in S6. And the curve, the holomorphic D curve going into Q5 actually maps to a line in Q5 if and only if the projection is actually a linear S2. So if it doesn't map to a line, then the projection is not a linear curve, is not a geodesic two-sphere. As long as you're not in the linear case, and it's important, I mean, this is an important special case that I'll come to in a few minutes. As long as you're not in the linear case, then psi, if psi is a holomorphic D curve, then it is the binormal lift of its projection. So it's uniquely determined by this pseudoholomorphic curve as long as it's not a linear curve. So a few things to say about the nonlinear D curves. The set of D lines, that is lines in Q5, is itself that is lines in Q5 that are tangent to the distribution D. It's actually a compact homogeneous complex manifold of complex dimension 5 because it's G2C modulo a maximal parabolic. G2C has two maximal parabolics that are not conjugate to each other. One of them, the quotient is Q5, and the other is this space of lines in Q5, tangent space of D lines in Q5. This was observed by Cartan a long time ago. It's a result of Cartan's, right? And as I was saying earlier, if you have a nonlinear D curve, then no, this is a new thing. If you have a nonlinear D curve in Q5, then it's actually non-degenerate in CP6. That is, it can't lie in a CP5. And as a result, you have all the Plücker relations that, for example, you can look at the ramification divisors of the curve as a non-degenerate curve in CP6, and it turns out that the ramification divisors are very constrained. The ramifications, the Plücker ramifications at order 1, 3, 4, and 6 are all tau, that divisor, and 2 and 5, they're all nu, computed for this guy, as I said before. Now, when C is compact and psi is a nonlinear D curve, its degree is at least 6, precisely because of this fact that the curve has to be non-degenerate. And Castelnuovo's bound doesn't allow it to be degenerate. And precisely because these ramification divisors are all there's no identity 0 anywhere. And the area turns out to be 4 pi times the degree of the curve in P6. This is, for example, C. Fernandez's paper. For example, if you look at the pseudoholomorphic, the one that I mentioned earlier that was written down by Sekigawa, that has constant curvature and it's homogeneous. Of course, it's G equals 0, and because it's homogeneous, tau and there can't be any vanishing. So tau and nu have to not have any vanishing, but beta has to be 0 then, from what I said before. So it actually has to have a holomorphic lift into Q5, and that lift has to be a rational normal curve because it's totally unramified. Now, the rational normal curves, the rational normal D curves, are in fact a homogeneous space. They are, if you look at in general, the symmetry group of a rational normal curve is SO3C, actually, or PSL2C if you want, but it's SO3C, and in fact it turns out that the space of these things is actually G2C, which acts on Q5 preserving D. It's this homogeneous space which is not compact. It's a non-compact complex homogeneous space of dimension 11. And this SO3C is actually the complexification of the SO3C that we saw earlier when we first wrote down sigma. So there's a large family of these things. And now I want to get to an application. The application is this. There exists a smooth pseudo-holomorphic curve of genus 0 and total area 4 pi and an associative plane E such that those two intersect in a single point. In particular, what that says is that the cone on C union with E is an associative cone with a single ray of singularities, a half ray of singularities. So this can happen in the decomposable case. So you can have an associative cone that whose only singularity is a half line. And here's how the proof goes. Quick proof. First of all, the generic rational curve in here, which is an element in here, is not invariant under conjugation. And the reason is that if it were invariant under conjugation, you can work out that that means the projection to S6 would actually be invariant under the antipodal map. And so the stabilizer will be a compact SO3 sitting inside the SO3C, you work it out, and it turns out that implies that it has to be constant curvature. But this is a 11-dimensional complex variety, and the constant curvature things are a real 11-dimensional subset, not complex. So the generic thing is not invariant under conjugation. So that means that you can choose a point in the curve such that minus x is not in the curve. Then the 4-parameter family of associative planes that contain, that pass through those points x and minus x, that family of planes actually foliates S6 minus the point x and its antipodal point. So what that means is that every y in the curve except x lies on a unique one of these planes, associative planes that passes through x and minus x. And there's only a 2-parameter points y and c, but this family of planes is 4-dimensional. So that means that So that means that the generic associative plane in F meets C only at X and nowhere else. And that's the proof. And clearly, in fact, if you choose E generically, it won't be tangent to C at X either. So they'll actually intersect, not transversely because they're both 2-dimensional and a 6-dimensional manifold, but non-tangentially. So you get a decomposable associative cone that has one line of singularity. I'm almost out of time. I will just say a few things about some further results and open problems. First of all, it's been known for a long time that every compact Riemann surface actually shows up as a pseudo-holomorphic curve in S6. And Fernandez showed that the space of nonlinear rational pseudo-holomorphic curves of total area of 4 pi d is non-empty for d equals 6 and then not 7, but 8 and above. And it has complex dimension d plus 5. And it's non-compact. We saw the 6 guy. But now the interesting question is, what is the Gromov compactification of this guy? Because the area is bounded, I mean, you don't have calibrations, you don't have a symplectic form, but you do have an area bound because they're all minimal. So any deformation can't change the area. So since it's bounded area, Gromov compactification says you should be able to compactify this. But the only way this can compactify is to break up into linear S2s, because there's no S2s of degree less than 6 except the linear ones. So that means that the compactification, the locus that you add when you compactify has to be some collection of, has to be some arrangement, some family of arrangements of two spheres counted with multiplicity, once you get counting multiplicity 6. But exactly which such arrangements appear is not clear. You might not like the example on the previous slide, which said that there's which produced an associative guy that's actually the union of two associatives that are themselves either non-singular or isolated singular point. But in fact, it turns out that there are elements in in degree 6 that when you project that, even though they're embedded in Q5, when you project them into S6, they actually have intersections. And the calculations are not complete, but it looks like you can actually arrange it so that there's only one intersection, so that you'll actually get an irreducible associative cone that has only one half line of singularities. And that's where I'll stop. I'm out of time anyway.
Great. Let's thank Robert. We have time for a couple of quick questions, maybe, if anybody has any questions at this stage.
Do you know if these cones can be deformed to something non-conical, which still has the same kind of singularity structure? Generically, you would expect they wouldn't.
That's a good question. I don't know. I mean, I do know that certainly associative guys can have singular structures with where the singularity locus is an analytic curve, but I don't know an example that's nonlinear, that's not a cone, that has a half line. But I believe that Zhenhua Liu has given me an argument to say that there should exist examples that are not cones, that have singular loci that end in points. I haven't understood the argument yet.
I think Camillo's original motivation for the question that he asked Robert was to try to construct other interesting singularities by kind of exploiting at least the fact that you can change a G2 structure and keep a G2 structure. So they were more interested in interesting singular set behavior, but not necessarily exactly in the calibrated world.
I had a feeling there was some kind of general theorem that these, or in this case, these one-dimensional by codimension 2 singular sets had to be branched. Is there such a, or something, or some generic? But in your case, they're self-intersections, but they could also be branched.
Oh yeah, that's right. You can produce ones where the singular locus is actually locally looks like a line cross a ramified curve.
Hmm.
Right. You can certainly do that. Yeah.
Maybe that would be a good moment just to pause questions and reserve any further ones for the break. And thank Robert again.